Okay, well, it's a great pleasure to be here. I have to say, Cambridge has got a lot busier in the summer than when I was an undergraduate here in '74, so there weren't as many tourists or visitors at that time. And you didn't have to pay to go into all the colleges. So I want to talk about joint work with Alan Tesdall on some problems related to weak shock diffraction. And I mean, since this is a free boundary conference, just some general comments about shocks as free boundary problems. I mean, shocks are sort of interfaces and boundaries, but somehow there's something different characteristic about shockwave problems. I don't want to say they're more difficult than other free boundary value problems because, I mean, free boundary value problems are all difficult. But if you say they're more difficult, I won't disagree with you. So, and I mean, what are some of the problems? Well, one is the governing equations of quasi-linear conservation laws. And then if you have shocks, not only do they interact strongly with the solution on either side, but then the geometry and motion of the shock front affects the solution. So they're sort of fully coupled with the flow. So in that sense, you know, it's not really just an interface problem, it's a full PDE problem. Okay, shocks can also interact with each other at triple points and contacts and so on. And also shocks may appear and disappear in complicated ways. And so I specifically want to talk about here some connection with disappearance of shocks related to diffraction problems. And this leads to some very strange problems in matched asymptotics, which I haven't quite figured out yet. So I'll come to that as we go along. So here's kind of the basic picture that I have in mind. Namely, imagine you have a wall here and then a screen. Let's see. So there's a screen here, and then a shock. Imagine a shock comes in, hits the screen, and what happens then? Well, the instant shock will pass through. You'll get a reflected shock coming off the screen, and then you get this sort of picture where the shock will diffract around, and that's sort of what's illustrated up there. And what you see is the diffracted shock will come around and it will die out and turn into an expansion wave. And so the particular problem I'm interested in is what happens near that point S. How does the shock strength go sort of continuously to zero and then turn into an expansion? It's a self-similar problem, and I'm going to approach this by doing matched asymptotics. So near this point S, you can approximate the Euler equations by transonic small disturbance equations, and that's the problem I want to look at. So UTSD will come up a lot here. It's unsteady transonic small disturbance. So let me say a few words about that.
Was it picture on self-similar plane?
Yes, so, well, that was just at some fixed time, for example. So it would just expand, right? So this will just expand self-similarly. So it's a 2D Riemann problem. Yeah.
So this is the liquefaction wave this side, expanding wave?
Right, so what's happening here is, you know, you have, this is the undisturbed flow, this is the sort of compressed flow behind the instant shock, this is the doubly compressed flow behind the reflected shock. So you have an expansion going out here and an expansion going out here. Yeah. And so, and as I say, what's interesting to me is what's happening here where the shock turns continuously into the expansion. Basically, once you include nonlinearity in diffraction, you're always led to this transonic small disturbance equation up there. So you can think of x and y as to be local coordinates near this point. And okay, I hope this is clear enough, but roughly speaking, when you look at the structure of this solution, it's more or less a linearized problem inside here. The linear solution breaks down near the wave fronts and you get an expansion or a shock. And it's essentially one-dimensional most places. But these places here and here, you get both nonlinearity and diffraction become important. And so then you have to use a TSD equation. And somehow this is the canonical equation that combines nonlinearity and diffraction in conservation laws. So if everything's independent of y, you just get back to Inviscid-Burger's equation. And so you can think of it as a two-dimensional generalization of inviscid burgers. So the first equation, the ut plus half u squared x plus vy is 0. So you can think of u and v as x and y velocity components, or u is also pressure in this approximation. And the first equation is sort of a combined conservation of mass momentum, and the second equation is sort of an irrotationality condition that comes out of the asymptotics. Now, it's a little peculiar. This system is actually hyperbolic, although it might not look like it, but unfortunately time is a characteristic direction. So this is sort of the price you pay for this reduction from Euler to TSD. You reduce, it's still a 2 by 2 hyperbolic system, but its time is characteristic, and then the irrotationality is sort of the constraint on the initial characteristic surface. Integrable systems people would call this dispersion as Kp. If you put in KdV instead of Burgers, you get exactly this. But just to comment, the zero dispersion limit is not relevant for shocks. And in some sense, somehow these shock wave problems, I think, are strongly non-integrable. There's almost, I mean, it's very hard to do anything exactly with this equation. And as I'll show you, basically, we just have to solve it numerically to understand what's going on. So now, let me first comment, so going back to this picture, let me just first show you what happens at the top, where the reflected shock turns into the diffracted wave. So if you do some matched asymptotics around there, you get basically you get an inner problem for you get a 2D Riemann problem for the transonic small disturbance equation. And I won't go into all the details of deriving the matching data, but it's actually a 2D Riemann problem where you have one quadrant, the solution is constant in one quadrant, equal to 1, say, and then it's 0 everywhere else. And here's what the solution looks like. Unfortunately, it's rotated and reflected from the way I drew it here, but this you can think of, this is the instant shock. It turns into the weaker diffracted wave. The expansion wave is coming out here, and that's what the structure of the solution looks like near that point. And you know, another comment, you could figure out exactly the size of the region around here with that solution in terms of the shock strength. So that's something it's not hard to do for everything works out very nicely. Now, what I'm really interested in is here is what's happening down here. So here the shock strength, you know, the shock strength doesn't go to 0, it sort of changes from the incident shock to the diffracted shock. Here it goes continuously to 0, through 0, and the shock turns into an expansion. Everything is self-similar, so it's convenient to write all these equations in these self-similar variables. These are basically these are the sort of TSD analog of polar coordinates, without going into any details. And then this is what the self-similar equations look like in these coordinates. So the time's gone away. You just have these equations. It's not hard to see. They're hyperbolic if rho plus u is negative, and elliptic if that should be rho plus u is positive. They're mixed type equations, something like steady transonic equations, but they have variable coefficients. And more or less they're hyperbolic outside the diffracted wave, and then they're elliptic inside. So just to remind you, here's the picture, and then these equations are describing what's going on here. Now, what happens then is to get the sort of local problem here, you match with the outer solution, the linear solution in here. And what the linear solution looks like is it looks like an expansion wave on this side where y is negative, a compression wave on that side, and then the strength of that wave just goes continuously through 0 as it goes from compression to expansion. And in this setup, rho is essentially a radial coordinate, and then theta is like you could think of it like an angular coordinate measuring along here. So theta is going along here, rho is going along there. And you do you go through the asymptotics, and you end up again with the problem for this TSD equation. And then the key thing here is this matching data. U looks like alpha, theta root rho. So when theta is positive, this is like a compression. When theta is negative, it's like an expansion. And then you want to know what happens here. Now, one thing that's very peculiar in this problem is, notice I have the small parameter alpha is still in my matching data. And you can't remove that small parameter by rescaling. So it's a very peculiar problem. And this is sort of at the heart of the difficulties in trying to understand what's going on. Now, you can't remove the small parameter alpha. I don't know how to determine the size of the sort of transonic region around here by sort of standard asymptotic arguments. And this is sort of not really kosher from the usual asymptotics point of view, because we're looking at expansion as alpha goes to 0, and then I'm keeping the small alpha term in the matching data. So that's my first step to approach this. But these problems are all connected with the following thing, that the matching data in the PDE are actually self-similar in self-similar variables. So that's what's sort of the fundamental issue here. And that's not true in the other solution, other parts I showed you. So it looks like you could just solve this by reducing it to an ODE. So let me just show you the ODEs briefly, and then I'll explain that they don't actually work. So you get the following kind of, I've looked at this system quite a lot, but you look for self-similar solutions of that problem. You get a pair of ODEs, so it's a 2x2 system of nonlinear ODEs, variable coefficient. Coupling F is essentially the u variable, the radial velocity, g is the transverse velocity. And then you more or less have to solve a 2-point boundary value problem for these guys. So you have a condition at the wavefront and you have a condition at infinity. And one thing that's slightly odd is, I don't know if it's odd, but it's a difficulty. You actually have to sort of think about what, you have different solutions valid in the compression part and the expansion part. Now, I've tried to analyze these. I mean, if you just count boundary conditions, it looks like you have the right number of boundary conditions and things, but it's a nonlinear connection problem. So I think it should be possible to do some analysis, but I haven't been able to prove anything at this point. And there's various complications. You know, in the expansion side, Z is the wavefront, so everything degenerates at Z equals 0 and things like that. It's quite a complicated problem with a lot of structure. And then on the shock side, you have to solve this 2-point boundary value problem, and the shock location is an unknown parameter. So that looks sort of promising, except it doesn't seem like there's any solution of this problem. And the reason I say that is, if we solve that shock diffraction problem numerically, you don't see a self-similar solution. You see something that's highly non-self-similar. So this is a numerical solution. We have this parameter alpha that's sort of measuring the shock strength. And so here you have a shock changing continuously into an expansion. So the left-hand side is the U contours. You could think of that as pressure contours. The right-hand side is a surface plot. And what you see is the shock is sort of coming around, it's getting weaker, it's stopping, it's turning into an expansion wavefront where you've got to jump in the discontinuity. But the shock doesn't die out. The self-similar solution would say the shock would die out exactly at 0. That would be the sort of symmetry point for the linear solution. But the shock actually diffracts non-linearly into the expansion region. That's what the numerical solution looks like. This, as I said, this parameter alpha is non-removable, so you can sort of see more details if you increase alpha a bit. But really the relevant limit is alpha goes to 0, but I don't really know how to do that. Now, so this is alpha is 0.2, you see the same thing, and this is alpha is 0.3. And here you can sort of clearly see the shock coming around, diffracting into this expansion region. So one question I have is, what's going on here non-linearly when this shock really disappears? And the question is, one question I had is this: do you see the shock sort of being generated from focusing characteristics, for example, or you know, how does that shock change? And it seems to just die out exactly on the sonic line. And here's a blow up. So here's the shock. These again would be U pressure contours. The shock strength is going down to 0. It's about 0 here. It turns into an expansion there. And if you look at the profiles of the shock, as you say, yes, question.
So you say a shock dies on the sonic line. Where is it in the picture?
Right. So the picture would be something like this. You have this diffracted shock coming around. The linear theory would sort of say it switches to expansion right at this symmetry point, but it actually just dies out, goes a little further, and then it just merges continuously.
Sonic circle.
Right, so the sonic circle appears to go exactly into the end of the shock. So that's, you know, I wondered, could the shock somehow, you know, go inside or something like that, but that's not what seems to happen. And that's what this picture is showing you. So here's slices across the shock as you go down here. So here it's relatively strong, gets weaker. 0 is exactly where the sonic line is. So you can see it really just seems to disappear right on the sonic circle. So I mean, it sounds good, but all right. So I mean, so the question is this: does the shock appear or disappear? This is I guess the question is with the Cheshire cat appearing or disappearing. I mean, if you think about 1D conservation laws, then what happens? Well, shocks typically form by focusing, and if they get hit by strong expansions, maybe they can disappear, but that's kind of the atypical picture. You get shock forming. If you look at transonic flow over airfoils, my collaborator Alan Tesdall did some very careful numerics and shows that, you know, if you look at the shock at the rear of a transonic airfoil, it really seems to form by focusing of characteristics coming off the sonic line inside the supersonic region. So it's like a one-dimensional shock formation. Whereas this disappearance in these diffraction problems really seems something different. And I don't know exactly how to quantify it, but I want to say this shock is really disappearing as it diffracts, not appearing by some focusing, whatever that means. Okay, to finish, I just want to say a few things about how this relates to mark reflection. And this is actually the problem that got me interested in this issue of what happens when shocks disappear. So here's a picture of just a classical reflection. You have a self-similar problem. You have a thin wedge, a shock comes in, hits the wedge, and then for small wedge angles, you see this sort of glancing mark reflection pattern. So there's an instant shock, generates a diffracted wave, and you see this triple point where the instant shock, diffracted shock, and the mark stem all meet. If the wedge angle is very small, then this diffracted wave is weak. If it's the perturbation really of a shock just going along a wall with no reflection. And so Lighthill wrote a couple of really beautiful classic papers on diffraction of blast, and in particular in 1949 he studied the linearized theory of glancing mark reflection. And you just get sort of a linear problem for acoustics problem for that diffracted wave. And the linear theory has a square root singularity at the boundary, like we saw. That square root singularity is corrected to a shock in the nonlinear theory. However, the really fundamental feature, I think, of the Lighthill solution is this, that if you look at the strength of that singularity as you approach the triple point, it goes away. So it's like the shock strength goes to 0 in the linearized solution exactly as the diffracted shock hits the triple point. And it's related to the fact that you have oblique derivative boundary conditions behind the shock, and the oblique derivative goes tangent to the diffracted boundary exactly at that triple point. So that's somehow what's causing this degeneracy. Now, the question then is, okay, that's the Lighthill's linear theory. The question is, what really happens in the nonlinear theory?
So,
yes.
Triple point is a sonic point.
Well, in the linear theory, it will be, yeah.
Linear.
Yeah, but right, it's it'll be slightly ahead, I mean, so I'll show you. So essentially what we're asking is what happens to reflection. So this is a Mach number wedge angle. There's two parameters, the Mach number of the instant shock, the wedge angle of the angle of the wedge. And very crudely, if you look at how things behave in the Mach number wedge angle plane, sort of in the linear regime when you have large wedge angles or weak shocks, you get regular reflection. In the nonlinear regime where you have small wedge angles or strong shocks, you get Mach reflection. And we're looking at this limit as the wedge angle goes to 0 at fixed Mach number. And the picture I have, so somewhere near this triple point, there's a nonlinear region where these guys are all interacting. I don't really know, for example, how to estimate the size of that region for the reasons I mentioned before, but it certainly seems like you should get a transonic small disturbance approximation for what's happening nonlinearly there. The shock, more or less, so this is all now rotated, the shock is now horizontal and it behaves pretty much as a soft boundary where you have sort of zero pressure on the perturbation behind the shock. And then otherwise you're sort of imposing the same kind of data that I talked about before, where this sort of shock is coming in and dying out according to linear theory exactly at the triple point. Okay. But what I believe happens is that, as we saw before, the shock doesn't die out exactly where the linear theory says it does. It has to diffract a bit further. So non-linearly, this shock actually comes in and hits this triple point. And so you really get a triple point, not a shock disappearing like the linear theory naively might suggest. So here's a numerical solution of the TSD problem. So you should think of this. This is now the Mach stem, this horizontal thing. Here, it's a soft boundary. So zero pressure, if you like. These funny domains are just because we're solving these problems in parabolic coordinates, so you shouldn't worry about that. But so the picture is, here's the Mach shock, here's the diffracted shock coming in and hitting it. Okay, now you can see this stuff here. This is not numerical noise. This is showing you what's happening according to the nonlinear theory at this triple point, and here's a blow up of that. So in a very small region near there. So this is a phenomenon I've seen before with Alan Tesdell, and he's got it even in full compressible Euler. So we call this a Goodly Mach reflection. So I don't have time to talk about it all, but you see this structure coming here. So what's happening here is the diffracted shock is coming in, hitting this boundary. It's a soft boundary, it reflects off as an expansion wave. That expansion wave pushes out a supersonic bubble in the elliptic region. Comes out, it reflects off the sonic line. When it reflects off the sonic line, it reflects off as a compression wave. That comes back down, hits the Mach stem, or this boundary again, and then the whole pattern repeats itself. So we call this a Goodly Mach reflection. It explains related to sort of von Neumann paradoxes and things like that. And the conjecture is maybe there's actually an infinite, I mean, this is what I believe, there's actually an infinite sequence of points here because related to sort of shock-free transonic flow past airfoils, you don't expect this sort of supersonic bubble to be terminated smoothly. You expect pretty much generically to have a shock at the rear and then. All right, this is still kind of somewhat heuristic, the derivation, because I still don't know how to really systematically do a lot of the asymptotics. I believe this is the right solution, but to really derive it, figure out, for example, what the size of the transonic region near the triple point is, I don't know how to do that either yet. But so just in conclusion, the behavior of these weak diffracting shocks when they die out is not so easy to analyze. I don't really have a completely systematic theory, but in the sort of this case, it's maybe a little dull. All that happens is the shock diffracts non-linearly a little further than the linear theory would predict, and it seems to die out exactly on the sonic line. For the shock reflection problem, it suggests that you're always going to see this Goodly Mach reflection in the glancing limit, independent of Mach number. So I did previously with Alan computations with sort of small, weak shocks, but this would say in the glancing limit, independent of the Mach number, this is sort of going to be the generic behavior that you see. So that's it. Thank you very much.
Go to the last pattern. You have developed numeric scheme to compute full compressible.
So Alan, so there's a paper by Tesdall and Sanders and Keyfitz. They did some for full compressible Euler, and he's recently done. Alan has recently done some more full compressible Euler computations for slightly stronger Mach number shocks.
Oh, so very clear from numerical.
Right. So I mean,
Subsonic bubble.
yeah. Well, so we first did this for TSD, and we saw about 5 patches here. So I think there's maybe, it's harder to get that many, maybe 3 of these patches or something in full compressible Euler. Alan also did it for nonlinear wave systems. So, I mean, there's lots of independent computations that I think, you know, I'm not everybody is convinced by this. There's other, you know, other people that say there's just a goodly reflection with none of these extra stuff. But I mean, Alan, so there's some papers by Vasilev and Kryko that show the expansion fan. But Alan did recently did higher resolve computations for their parameter values, and when you look at that, you find more patches and more triple points. So, but well, not everybody agrees with that.
There's some literature about viscosity near these points, isn't there?
Yeah, so I'm not right. I mean, I'm not sure about the literature referring to, but there's 2 things. One is, of course, if you put viscosity in, if there's a little bit of viscosity, this structure gets completely washed out, of course. And that's why numerically, if you're not really resolving, these calculations are done by putting enormous number of grid points right around the triple point. So yeah, if you put viscosity in, this all gets washed out. And that's also why this wasn't observed experimentally. So because...
I was thinking more of your first problem.
Oh, which one? This one? Well...
there's no hope of any similarity in it with viscosity.
Right. I mean, that gets completely broken. I mean, also, I mean, I'm ignoring separation and things like that, but...
Just near where the shocks are.
Yeah, so...
I just seem to remember some Russian guy.
I'd be interested to see that. I mean, the only comment I would make is if one you could do the asymptotics and include viscosity, and then you get what you might call the ZK equation, but that's no easier. I mean, I don't really know how to solve that problem either. I'm sure it would have, I mean, you'd have smooth solutions, of course, but whether you could really extract any information out of it, I don't know. Yeah.
Can you show me in your picture where V is greater than 0 or where V is smaller than 0?
Oh, the V or the U? The
V.
Right, so, well, yeah, I didn't have V plots, but basically the velocity would be going, I mean, you're going to have a velocity roughly radial, so you can see the V component is going to switch signs. If you're asking about the V would be the Y component in my... Yeah, so I mean, the flow will sort of be going out and like this.
So the region is divided into 2 parts.
Yeah, I mean, there is, yeah, you mean ask, is there some line here where, yeah, I'd have to think more carefully about the V. Somehow the V in this framework is sort of a secondary variable. You can just reconstruct it from the U, the pressure. So I'm not used to thinking about the V, but I think, yeah, basically it's, I mean, I think there'll be some flow here, some flow there. I don't know exactly what it would look like.
But for you, where is the greater than 0?
Sorry, the U?
For the X component.
The X component or the... Yeah, so I mean, here it's a compression. The U is going to change. Yeah, I mean, you can see in this problem. So this is the U. So here the U is sort of positive, and then it's decreasing, and then here it starts at 0 if you like the sonic value, and then it goes negative. So I would think of this in terms of pressure. There's a low pressure region here going to the pressure at the wavefront and a high pressure region at the top that forms the shock. And here this is the expansion. I'm not sure if that answered your question.
Let's again.
I should start right away.